Hello everyone, we will continue with the geotextile strength calculation part. In last class, we have discussed the geotextile strength related to bursting type loading and also the tensile related loading condition. Today, we will discuss the other type of strength condition like puncture, tear and impact. First, let us start with the puncture type condition. So, geotextile during its placement must survive the installation process. It is not only the performance during the use, long term performance, but during installation it may counteract different types of stresses. So, puncture is one of them. Basically, it is a survivability type condition which is critical in all type of application. Without it, the best design and best type of geotextile may fail. Suppose a best type geotextile and very good design criteria is there, but due to some mishandling there is a puncture created, that means total structure will fail. So, we must know the puncture resistance of geotextile. So, in this regard, so where sharp stone, tree stumps, roots or different types of debris, this debris contains different sharp objects, and apart from this there are different types of objects which are present under the ground where geotextile is placed. So, these objects may create puncture in the geotextile, where the vertical forces are exerted by these objects on the geotextiles which may create puncture. So, we must know the puncture resistance of geotextile for all these survivability characteristics. So, this survivability function is very important. So, whatever conditions we have discussed, the vertical force here it is a this vertical force is exerted on the geotextile which is gradually tightening around the protruding object. So, it is a there is some object. So, it is vertically moving upward and it is getting tightened, the geotextile is getting tightened due to the pressure applied from the top and the damage occurs. And this damage occurs basically tear type of damage. So, we can actually get the tear resistance also. So, theoretically the expression here is that P required. So, that puncture resistance F required is given by P dash, which is the tire inflation pressure, dA is the diameter of stone, dA square, S1, S2 and S3. What are these S1, S2, S3? I will just explain. So, F required here is the required vertical force to be resisted. So, this is the vertical force here, this has to be resisted, that is the required puncture resistance. So, whatever this vertical force by the stone or sharp object, that is the F required. P dash is the pressure exerted on the geotextiles, which is approximately equal to 100% tire inflation pressure for small stone thickness. If the stone thickness, this is the road stone thickness, and if it is the geotextile. So, for small stone depth, stone thickness means for the smaller depth of geotextile placement, this we can assume as 100%. If it is larger depth, we are placing geotextile at the larger depth. So, this may reduce little bit. dA is the again the average diameter of the sharp object here, the stone or something. So, this is the average diameter of the puncturing aggregate or sharp object. S1 is the protrusion factor. Protrusion, what is protrusion factor here? HH by dA. HH is means that the amount, the extent it is entering, penetrating, that is a height H, the it is penetrating inside the geotextile, and diameter of the stone or object. Okay. HH protrusion height, typically it is a less than or equal to the diameter of the stone. S2 is the scale factor adjusted as per the ASTM standard test, the diameter which we use using 5 by 16 inch diameter puncture probe, which we use as per ASTM D4833. In that we use the puncture diameter as 5 by 16, that means it is coming out to with 0.31 by dA. So, dA here its assumption, it is the diameter of the stone, and in our test we assume it is a 5 by 16 inch. So, that S1 is the scale factor, just we have to scale up or scale down depending on the actual diameter of the stone, that is S2. S3 is the shape factor of the stone, which is adjusted to the flat puncturing probe as ASTM D4833. That as per ASTM, the puncturing probe is flat, but actual shape of the stone is not flat. So, from there we can calculate the S3, which is the adjusted shape factor. So, this is nothing but 1 minus AP by AC. AP by AC is it is a sphericity of the stone, which is giving the value of 1 that is 0.8 for Ottawa sand, 0.7 for a round of bank gravel, 0.4 for crushed rock, 0.3 for short rock. So, these are the value, standard value given. From there we can calculate the S3 value, that is the shape factor, it is a adjusted shape factor. Okay. And AP here, AP is the projected area of particle and AC is the area of the smallest circumscribed circle. So, from there we can calculate the actual shape factor or adjusted shape factor. So, if we know all this parameter, we can calculate the required vertical force to be resisted. So, let us see here. So, let us try to calculate what is the required puncture strength or vertical force to be resisted, and B, a factor of safety against the puncture of geotextile from a 2-inch stone by a loaded truck with tire inflation pressure of 80 psi travelling on surface of stone base. So, what we have to calculate? The puncture resistance and the factor of safety with the given dimension of stone and the tire inflation pressure is given. The other data which are given here, geotextile has an ultimate puncture strength of 45 pound according to ASTM D4833 as I have already mentioned, and assume 0.33, 0.155 and 0.6 for S1, S2 and S3 respectively. These are the value given here. So, we can use the earlier equation to get the puncture strength. So, given here dA is given, ultimate strength is given. So, the required puncture strength of geotextile or vertical force to be resisted is given by the earlier formula. P dash is given here 80, dA it is given here, it is a 2-inch, S1, S2, S3 are given. So, from there we can calculate the F required, directly we can use. So, 80 2 square 0.33 is given here, 0.15 is for S2 and 0.6 for S3. So, from there we get the value of required puncture strength equal to 9.82 pound. Now, coming to the next is the factor of safety. Here factor of safety is nothing but the ultimate factor of ultimate puncture strength by required puncture strength. So, ultimate strength is given 45, 45 is the ultimate puncture strength, and required we have calculated 9.82. So, effectively factor of safety we get here is 4.58, that is the factor of safety we get. Now, the alternate way of getting puncture resistance is that given by, which is the theoretical approach, it is Fv equal to pi dn multiplied by Hn multiplied by P dash multiplied by S dash. Now, let us see what are these parameters. Fb is the Fv is total vertical force imposed on the fabric adjacent to the puncture. So, in actual field condition, the total vertical force, that is the vertical force inserted on the geotextile, it is imposed on the geotextiles, average diameter of aggregate dA, dn is the average diameter of hole, that is the dn, this is the average diameter of hole is dn here, which is given by, it is approximately here equal to dA. This average diameter of hole, it is nothing but it is the average diameter of stone, because that hole is created by the stone, because the stone is pushing the geotextile upward. So, here the assumption is that the average diameter of hole is equal to average diameter of stone, and propagation height. So, propagation height h n, this h n propagation height is maximum propagation height can be equal to the diameter of the stone. Suppose this is one geotextile, okay, and we have one stone here. Now, in the next condition, when the pressure is applied, this geotextile can, this stone can propagate maximum this height. So, this height, it is h n is nothing but the diameter of the stone, and also this d n average diameter of hole, this is the average diameter hole, this average diameter of hole is this one. So, if I draw here, this is the hole diameter, this is again will be equal to d A. So, d n is equal to d A and h n again equal to d A. So, the hole diameter is equal to diameter of stone, and this height, propagation height is again equal to diameter of stone, because the propagation and the penetration are basically due to the stone. So, if we assume d n equal to d A and h n equal to d A, in that case this portion will be d A into d A equal to d A square, it will be d A square. So, if we use this, it will be this formula will become, so F v, the total vertical force, is equal to pi d A square p dash and s dash. So, propagation height and average diameter of hole are typically equal to the diameter of aggregate or stone. So, here we are getting F b value. So, pressure exerted on geotextile, it is equal to the tire pressure, and S dash, here S dash is shape factor of stone, which is equal to 1 minus A, 1 minus S is the sphericity. Sphericity, what is sphericity? It is a ratio of projected area of the particle and the area of smallest circumscribing circle around the particle. That smallest circumscribing circle around the particle. So, that A p by A c is the sphericity, and S value it is given 0.7 to 0.8 for sand, that is standard value given, 0.4 to 0.6 for crust rock and 0.3 for short rock. Now, for round shape, its shape factor is equal to 0 or blunt shape. For sharp object, it is a 1. Now, let us see, this is a sharp object, suppose this is a sharp object. Okay. So, projected area of, here projected area is, say here this is the projected area, you can say A p is equal to 0. So, here S will be 0 by something A c, okay, will be 0. So, S is 0. So, for sharp object, if S is 0, so 1 minus S equal to 1. So, that is the for sharp object. For totally blunt object, so it will be equal to S will be equal to 1, where AP equal to AC for blunt object, AP equal to AC. So, S will be S equal to 1. So, if S is equal to 1, then it will be 0, S dash will be 0. So, for blunt object sphericity is 1, for sharp object sphericity is 0. So, accordingly the shape factor will get adjusted. So, from there we get the shape factor, and using this shape factor we can calculate the vertical force imposed on geotextile fabric. Okay. Now, the tensile force in geotextile due to puncture force is the vertical puncture force that can be converted into tensile force of geotextile by this formula. So, by this assumption we can calculate the tensile force on the geotextile from the vertical forces. Fv is the vertical force, puncture force, and T required is the tensile force on the geotextile, which is given by dA, diameter of the stone, and div is the initial void diameter of the fabric, that is the diameter of openness, opening diameter of the fabric. So, Fb is the total vertical force on geotextile, T required the total tensile strength of geotextile. So, Fb is acting in this fashion and tensile force will be in this fashion, tensile force to be. dA is the average diameter of the aggregate, and div the apparent opening size of geotextiles, that is the opening size of geotextiles, okay, which is very small. Now, from this relationships what we get here, tensile force in fiber of geotextile, that means tensile force exerted on geotextile due to puncturing, is that we have seen these two relationships, Fv by T required equal to dA by div, that we know, and also we have seen that Fb equal to pi dA square, P dash is the pressure, S dash is the shape factor. So, from there if we see, we can calculate the T required, which is Fb by Fv by dA by dV, and by just putting the value, replacing the value of Fv, we get the relationship is this, where dA will cancel out, 1 dA will cancel out. So, pi dA P dash S dash div. So, again here S dash is the sphericity, S is the sphericity and S dash is the shape factor of the stone. So, from this we can calculate the tensile force generated in the geotextile due to puncture, due to the upward puncturing force. Now, let us try to solve one numerical here. Determine the minimum tensile strength of geotextile when apparent opening size of geotextile is 0.3 millimeter. So, 0.3 millimeter is the opening size of geotextile. So, in a suppose this is a non-woven geotextile. So, average opening size will be 0.3 millimeter. Size of rock is given 35 centimeter is the size of rock, very big size rock. Sphericity of rock, which is S equal equal to 0.25 as we have seen. Tire inflation pressure 600 kPa and factor of safety is given 3. So, here we have to calculate the minimum tensile strength. Let us see. So, the problem here is based on tensile strength due to puncture. So, here we have created a puncture type situation, but we want to know the tensile strength, okay, because we know the geotextile opening size and size of rock. So, from there and pressure is imparted. So, that puncture like situation is created, but we want to calculate the tensile strength. So, we have to use the formula which we have already discussed. Here it is given that diameter of opening, that is opening diameter, that is apparent opening size, that means geotextile pore size is 0.3 millimeter and it is given kPa. So, we have to convert it to in meter. So, it is 0.003 meter. Sphericity is given as 0.25, diameter of stone is 35 centimeter, that is 0.35 meter. Tire inflation pressure is 600 kPa, here it is given 600 kPa, and shape factor is nothing but 1 minus sphericity, and sphericity is given here, it is a 0.25. So, shape factor of the rock is 0.75. So, we can use this equation directly to get the required tensile strength. So, this is the, so pi 0.35, 600, 0.75 and div is 0.0003 meter. So, we get the value 0.14844 kilonewton, and which is nothing but 148.44 Newton, and we know the factor of safety. This is the required, this is the value which we get, which will be required to sustain in these conditions, in the field condition. So, in the field condition minimum value required is 148.44, otherwise we will not be able to survive, and the product which we get with the specification that factor of safety required is 3. So, it will be definitely 3 times to that of this. So, the factor of safety is 3. So, actual tensile strength required is 445.32, that is the minimum tensile strength we require in the geotextile to get that minimum 3 factor of safety with the following conditions. So, first we will require from the given condition, we will calculate the required tensile strength for survival under this condition, and then we will get the value of the actual tensile strength of the product. So, this is the actual tensile strength. Now, the tear condition, as I have mentioned, it is exactly similar to puncture condition. So, basically the tear in a geotextile, it occurs during the just after the puncture. So, the tear strength of geotextile can be expressed by Koerner using the same equation. T tear is directly pi dA square P dash and S dash. S dash is the shape factor here, okay, which is nothing but a puncture strength. As I have already mentioned, P dash is the stress at the geotextile surface which is less than or equal to the tire inflation pressure, and dA is the average stone diameter, S dash is the shape factor of the stone. As already been mentioned here. So, these are the parameters which has already been explained. Okay. So, sphericity AP by AC. So, same shape factor we can use here. Now, let us try to solve the equation. So, it may be puncture strength or sometime it can be asked the tear strength. Okay. The crust rock of average diameter 0.375 inch and shape factor is 0.4 for crust rock as per Koerner. So, that is the was laid over geotextile with tear puncture strength of 160 pound. So, tear strength is known. If the truck tire inflation pressure is 95 psi, what will be the required tear strength and what will be the factor of safety. So, here assumption is that contact pressure is 100% of tire pressure. So, normally contact pressure is little bit less or less than tire pressure, but for simplicity we can assume 100% of tire inflation pressure. The solution. So, here given the diameter dA of the average diameter is 0.375 inch of the rock, shape factor is 0.4, tire inflation pressure is 95 psi and allowed tear strength is 160. So, this is the allowed tear strength. So, required tear strength is this is nothing but a puncture strength which is equal to 16.8 pound. So, pi multiplied with 0.375 is the diameter of stone and 95 is the tire inflation pressure, 95 psi tire inflation pressure, shape factor directly it was given and diameter is 0.375. So, from there we get it is a 16.8 pound. So, factor of safety which is equal to allowed tear strength by required tear strength. So, allowed tear strength is given is 16.160 and the required tear strength is 16.8. So, dividing 160 by 16.8 we get 9.52 as the factor of safety. So, after puncture and tear, the next strength related calculation is the impact resistance, which is very important during the application, during the laying down of geotextile, but during its application under the ground this type of situation may not arise. The resistance of geotextiles to impact is as much a survivability criteria as it is a separation function. So, it is a basically survivability criteria, it is not basically impact is normally not we counteract during the application, during the use. So, yet it may in many instances of separation geotextile must resist the impact of various objects. So, there will be different situation where geotextile will counteract the impact type of situations. The most obvious one is that of rock falling on it, but there are also situations in which construction equipment or material can cause impact and it may damage the geotextile. In case a rock falls freely on the geotextile from certain height, geotextile resists the impact and it may sometime get damaged. So, this fall, this is geotextile, a rock is falling on it freely, and typically this fall is due to the gravitational acceleration. So, gravitational energy is generated and we measure this gravitational energy on the geotextile. So, the problem here is the free fall. So, problem is one of the energy which is mobilized by free falling of object of known weight from known height. Okay. That is the, and rarely there will be a situation where someone is intentionally impelling on some objects on the exposed geotextiles. This type of situation rarely happens. So, some additional force is normally we do not add. So, only gravitational energy is calculated for impact resistance. So, there is normally do not apply any force, it may get dropped only, okay, during the impact type of situation. So, here that is why only gravitational energy is calculated. So, energy here it is we know the potential energy is equal to m, g and h, where E is the energy in joules, m is the mass of rock in kg, h is the height of fall in meter and g is the acceleration due to gravity, it is a 9.81 meter per square centimeter. So, here the V is the volume of the rock and rho r is the density of the rock, which is nothing but the specific gravity of rock multiplied by density of the water, and r is the radius of rock, Pw is the density of water. So, radius of rock. So, if we get this V, if we assume it is a spherical. So, 4 by 3 pi r cube is the volume, okay. Rho r is the density of rock, and from there by just by rearranging we get this value r cube, that is the radius cube. So, dA by dA cube by dA is the diameter of rock, and from here we can calculate. So, replacing rho r by specific gravity of rock and density of water. Specific gravity of rock is typically 2.77 is the specific gravity, and finally we get this equation pi dA q by 3 rho w specific gravity of rock, g and h. So, if we know these values, we can calculate the energy, that is impact energy generated due to free fall of any object, sharp object. So, when the rock falls on a geotextile laid on soft soil, soft sharp soil. So, here there is a condition. Now, let us see, it is a hard surface. very hard surface, another is very soft surface, very soft surface. Okay. And we are laying geotextile. So, this is geotextile, we are laying on it, this is geotextile, and you are, suppose one sharp object is falling and here another sharp object is falling. Here this is sharp object, due to this softness, this is after falling here, the impact energy which will be generated here is mgh, as we have impact energy, it will be 100% impact energy will be absorbed by here by the it will be imparted on the geotextiles. But if it is on the soft surface, this will get deformed here, and the subsoil will absorb little bit. So, that is the actually it is called reduction factor, but by or modification factor. So, when the rock, and it has been proposed by Koerner in 2005. Okay. So, that effect on softness effect will reduce the impact energy, effective impact energy on the geotextiles. So, when the rock falls on geotextile laid on soft subgrade soil with lower CBR value, California bearing ratio, that we have already discussed. So, lower CBR value, the geotextile deform. So, it due to deformation it resists higher extent of impact energy. Therefore, it is necessary to determine the modification factor. So, which is proposed by Koerner by, this is the typical curve. Here CBR value, California bearing ratio value, higher the value means the harder the surface. So, at lower value, so modification factor is very high. That means that effective the impact resistance, impact energy will be reduced by that value, and it will become typically around 1 for very hard surface. So, modification factor is the energy, the maximum energy developed that we have seen in the that equation, whatever we have seen, that is a maximum energy developed due to gravitational, that it is a gravitational energy on the hard surface, and E required is the required impact energy of geotextiles. So, that is the E by E required, and here is higher the modification factor, lower will be the required energy. So, for a very hard surface it is typically around 1. So, this is a very hard. So, CBR value is 20 and above, it is very hard. So, here you can see this is typically around 1. So, for very hard surface it is 1. So, in that case modification factor is 1, means required energy, impact energy is equal to maximum impact energy developed on geotextiles. Okay. So, now let us see, we have to calculate the mobilized energy due to free falling of rock of 300 millimeter diameter from a height of 1.5 meter on geotextiles. That is the requirement. So, and next is that if CBR value of soil is 5, the allowable impact strength of geotextile is 40 joule, calculate the factor of safety. So, let us see. So, dA is the diameter of the rock, 0.3, H is 1.5 and mobilized energy dA pi dA is given here, rho w is 1000 water and specific gravity of rock is 2.7, G value is known, H is 1.5. From this data we can calculate the mobilized energy and it is coming out to be 561.7 joules. So, this is the mobilized energy. So, which is mainly due to gravitational force. Now, we know that CBR value of the subsoil is 5, it is a soft subsoil, that means there will be some modification factor. Allowable impact strength of geotextile is 40 joules. So, 40 joules is actually it is a allowable impact strength, that is the maximum impact strength allowed. So, maximum energy developed as we have seen earlier 561.7 joule, that is the maximum energy. Now, from this modification factor curve by Körner 2005. So, CBR value is given 5. So, for 5 CBR value we have to calculate the typical modification factor. Here from this curve we have calculated this modification factor is coming out to be typically around 12. Okay. And this modification factor equal to E by E required. So, E required we have got is 46.8. So, maximum energy is 561.7, but due to modification factor, due to soft subsoil, actual the impact resistance required will be reduced to 46.8. That much impact force is actually generated in the fabric. So, the factor of safety is E allowed by E required. E allowed is coming out to 40, that is the maximum allowable impact strength, and required impact strength is 46.8, that is the actual it is generated. So, it is coming out less than 1, impact that factor of safety is less than 1, which implies that during the with the given condition and given material characteristics, this factor of safety is very low, and so the conclusion is that very low factor of safety. So, the geotextile will get damaged in this condition. So, what we have tried to discuss here, we have tried to understand different practical implication of geotextiles, how to calculate with the given conditions, given practical condition, how to calculate the stress generated, different types of stress generated in the geotextiles, and how to select geotextile based on the given or targeted factor of safety. So, we will stop here. Thank you.